Okay, so all right, so I had this homework problem asking if the derivative exists. So uh, especially for piecewise functions, the go-to definition of the derivative would be well, f prime of 0 is the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Um, so, okay, what do I do? What do I do for f of x? As you approach 0, what function am I looking at as I approach 0? And audio's okay now? Not choppy? Oh, did I not? Okay. I forgot to share my screen. Sorry. Okay, can you see it now? Okay, so can you see it now? So as I approach 0, what does f of x look like? Remember, I don't care what's actually happening at 0. Right? What the piecewise tells you is that, like, this is what's happening at 0, but who cares, right? Who cares what's happening at 0? That's what this says. Who cares what's happening at 0? We only care about what's happening around 0. So that's why we put x sine x, or 1 over x. And then what's f of 0? Well, it's 0, and divided by x. First of all, is this continuous, by the way, while we're here? Is this function continuous, f? Forget f prime for the moment. Is f continuous? Yeah, by the squeeze theorem, right? So if you take this limit to 0, you get 0 by the squeeze theorem. However, the derivative does something fails, right? What happens at 0? Look at what's happening at 0 for the derivative, right? Sine doesn't approach anything as it goes to infinity, right? 1 over approaching 0 is the same as just the angle approaching infinity. But sine is oscillating, so it never approaches something. So if you had this question for homework, either it was already due or it's due tonight, so there's the answer. But any questions on that? So the idea, if you were to kind of sketch this, what is x sine x? Well, when we did the squeeze theorem, we saw that it's always bounded by these by y equals x and y equals negative x, right, by the squeeze theorem. Right, this is negative x less than x sine x, or sine of 1 over x. Right, this was the start of the squeeze theorem. So what does the picture look like? Something like that. The idea is that the derivative does not approach something. Like if you were to draw tangent lines, if you were to zoom in towards 0, right, the tangent lines are not approaching anything, right? They're going up, sometimes they're going down, they might flatten out somewhere, but they're not approaching a specific slope. So that's why the derivative does not exist. Any questions about that? So later in this class, we'll actually, today, we'll actually calculate the derivative of this explicitly. And we can see why it doesn't exist at 0. Or it turns out its limit doesn't even exist. Okay, so let's think about this function, this limit. So I want to do this just for practice for quotient rule mainly, but this will help us kind of understand what sine of x over x looks like. Okay, how do you take the derivative of a quotient? So which do you take derivative first? That's a product, Andrew. Yeah. So yeah, the main thing to remember is always take the derivative of the numerator first. Yeah, so it's the derivative of the numerator is cosine, and then times the denominator, minus the derivative of the denominator, which is 1, times the numerator, over the denominator squared. Okay, so how do you solve this limit? X cosine minus sine over x squared. Any ideas? Do you see anything nice? Any identities or? Yeah, you'll probably have to use a sine of x over x, right? So how can you deal with that? Maybe split it up. If you split up the fraction, what do you get? You get cosine over x, because one of the x's, this x gets canceled, minus sine over x squared. So now when you use the sine over x squared the sine over x identity, what's left over once you take the limit? Like once you actually do the limit, what's left over? Well, there's only one x left in the denominator, right? It's x times x, and you're just left with 1 over x. So now, you get cosine minus 1 over x. Any remember how to solve this limit now? Anyone remember? We did this one before. I believe we did it when we were doing the derivative of sine or cosine. I'll give you a hint. The step is very similar to conjugate step. Right. You recognize that this is one of the factors of the difference of two squares. And by doing that, what you get in the numerator is cosine squared minus 1. Which is what? What's cosine squared minus 1? Good, it's negative sine. right? If 1 minus cosine squared is equal to sine squared, right? If you reverse the subtraction, it's negative. Okay, so what's the last thing we can do here? How can we simplify this more? So we can't plug it in yet. We can't just plug in 0, but we can do one more thing. Yes, we can use that nice identity again, the sine x over x identity. So that goes to 1. Then we get negative sine x over cosine plus 1. And what's that limit? What is that equal to? What's sine of 0? Right. What's cosine of 0? Yeah. It's limit 0. Okay, so what does this mean as a picture? So the derivative of sine x over x, this tells you what tangent lines are doing in the picture. So here's a rough sketch of sine x over x. Something like this. Well, not quite. It oscillates towards infinity, because if you take the infinite limit, you can see by that it approaches 0. Everyone see that? If you take the limit as x goes to infinity or negative infinity, do you see why it's 0? Can someone tell me why, actually? Why is the limit 0? Anyone? No, not divide. Well, remember the sine x over x identity is only true for x approaches 0. So you won't really get anywhere when you divide by x. You get sine x over x again, right? When you divide by x. That step would be okay if you're taking a limit to 0. Not sine of infinity. This is squeeze theorem. Sine x over x, you can bound it between x and 1 over x and negative 1 over x. And these both things go to 0 as x goes to infinity. So this would be that would be like sine of 1, that'd be 1 over x. That's kind of the picture of what's going on. Anyway, so what we just proved here in the derivative is that these tangent lines actually approach something. They approach being flat. So this is the derivative approaching 0. Derivative approaching 0. That's what this says here. When we took the derivative and we took the limit to 0, the limit was 0. So the tangent lines are actually flattening out. While in this one over here, when we looked at the derivative at around 0, if we just included 0 as a point, they don't flatten out. Right, so this is the derivative, the limit of the derivative at 0 doesn't exist, but here the limit of the derivative exists. So just two interesting functions there. Okay, so any questions? So this is just a quotient rule. Just kind of understand what the derivative is, kind of a little review. Okay, if not, today we're going to focus on how to find the derivative of composition functions. So just as a motivation, does anyone remember how to find the derivative of sine of 2x? Before any other rule that we haven't learned yet. Good, yeah, double angle rule. So yeah, so we don't treat this as a composition because we don't have that rule yet. But by the double angle formula, we can treat this as 2 sine cosine. So what rule can we use next before product rule? What rule would make this easier to do before using the product rule? An often overlooked rule. Anyone? Yeah, we can use the constant rule, right? Since we have a factor, that's a number, a constant, we can take that out and treat this just as 2 times whatever the derivative of sine times cosine is. Okay, so now we have the product rule, which someone suggested before. So you take sine. What's the derivative of cosine? What's the derivative of cosine? Good, negative sine. While we're at it, what's the derivative of sine? Cosine, good. Okay, so what is this expression here? 2 times cosine squared minus sine squared? What is this? This simplifies to something. Right, it is cosine 2x. And yeah, you can't factor -1 because they don't both have -1. If they both had -1, then it would just be right, -2. Right, but since only one of them has the negative, that means it's a double angle formula for cosine. All right, cool. So what is our motivation today is, well, did we have to know the double angle formula for sine to do this? Right? What if we had something like that we don't have a nice formula, angle formula for, like sine of 1 over x? Right? What is the reciprocal formula? I don't know. That might be something hard to figure out, a geometric formula. But instead of having to do that, let's try to deal with composition functions. Can someone give me an intuitive idea what a composition is? What does it mean to take a composition of a function? What is f? Yeah, what does that mean, f composed of g, like intuitively? There's two ways to interpret this. Okay, yeah, so you put a whole function in another, so that would be like plugging in g into f. Plug in g of x into f of x. Good, yeah, I like that. The range of the function enters as the domain of the other. Yeah, so a picture of that would be like, if this is x land, and this is g, so this is the range of g, and then that's the domain of f. Yeah, I like that. So these would be kind of the two ways to understand what a composition is. They're equivalent. Plug in g of x into f, and then the range of a function, the range of g, enters in the domain of f. Yeah, good. Okay, so the goal is, what is the derivative? So, as with anything, so first of all, how do you calculate f of g of x? It is defined as like if you have a value f of g of a, you plug g of a into f. So knowing that, knowing how to find the function at a point, now we can use our derivative formula, right? So let's do it. F of g prime of a is equal to the limit as x approaches a of what? Of f of g of x. So this is f of g of x minus f of g of a over x minus a. Okay, so now I don't see much I can do here, right? You can't really simplify this at all, right? However, let me ask you this. What can I multiply here in order to pop out a g prime of a? I notice that if I multiply something here, I can get a g prime of a. What can you multiply to get g prime of a? Well, hint, this is the denominator. what would the numerator be for it to be g prime as x approaches a? Almost, not just g of x, right? If it's just g of x, that's not the derivative, right? But I need something else here, right? So what would give me g prime? Good, yeah. So it would be g of x minus g of a over x minus a. This gives you the derivative, right? Because this limit is going to a. So by doing that, we can really separate our problem into two components. We have f of g of x minus f of g of a over g of x minus g of a. And then this becomes g prime. Now why is that nice? It's because this looks like a derivative, right? Like you have this thing is equal to this thing, and what you're plugging in is equal. So this looks eerily like a derivative. So that's why we did this step here. What was wrong with this limit here was, well, usually derivatives, right? These things need to be the same, right? G of x minus g of a over x minus a. The thing you plug in, x value needs to be the same as the x value here. So by multiplying by this term, we were able to bring in the term that we wanted. This is the term that we wanted here. Okay, so we're going to do something that's often used, and we'll use a lot later, but we're going to change variables. So this is what we're going to do. We're going to let g of x equal u. So this is a new variable u. So what do we get if we do that? This term in the limit, right, it's a substitution, good. Right, this term in the limit becomes f of u minus f of g of a over u minus g of a. Okay, can someone give me some info about this function? This is a function now. This looks interesting. This should look like something. Does this exist at g of a, by the way? Does this function exist at g of a? If you plug u equals g of a, does this exist? No, right? You get a 0 in the denominator. You get 0 over 0 if you plug in u equals g of a. So u does not equal g of a here. But can someone tell the limit? As u approaches g of a, what is this approaching? Here, maybe let's use a different letter. Pretend u is x now. So this is what substitution is. I'm just using a new letter because x wasn't helpful. So I'm using a new variable u. Okay, so as I approach u to b, what is f of u minus f of b approaching? over u minus b approaching. Remember, just pretend u is x. What would it approach? What does this look like? This should be ringing a lot of bells. What does that look like? So again, just get rid of the u. What does it look like? Use the placeholder. What formula is this of? It's a formula of some thing we've been working on for the past couple weeks. Yeah, velocity, or what's another term we have? A more general term. It's a derivative. Yeah, precisely it's the derivative at b. Right? So what we can do is we can construct a function such that it's continuous. Since we know the limit as u approaches b is precisely the derivative, then we can construct some new function h that is continuous. So for when u is not precisely equal to b, it's equal to this quotient. And then we just force it to be f prime when u is equal to b. Why is this continuous? It's precisely because the limit is actually equal to what's going on at b. Okay, so let's bring our variables back. So we let g of a is equal to b. Okay, so let's bring it back, and we get the limit as x approaches a of h of g of x, g prime of a. What is the limit as x approaches a of h of g of x? As x approaches a, what is u approaching? U is approaching g of a, which is equal to b, right? Now, what's that limit? As u is approaching b, what is h approaching? F prime of b, good. And then plug back in variables. What is f prime of b? It's precisely f of prime of g of a. Okay, so what was the whole point of this? Is that, so our goal was to construct a continuous function. Why? It's because we know a property of continuous functions is that the limit of a continuous function is just plug it in. So we construct this continuous function h of u, where if I take a limit, it just equals to the value at that point. So precisely h of b is equal to f prime of b. So why is that nice is when I bring back my variables, h of g of x, right, I'm plugging u equals g of x. As I approach x equals a, u is approaching g of a, or b, which gives you f prime of b, which is g of a. It's a bit of a mouthful, but it's the rough idea. This is called the chain rule. So f of g prime of x is equal to f prime of g of x, g prime of x. This is called the chain rule. It may look intimidating, but as we do, examples, it will get less intimidating. So any questions on that? So let's just do some examples to get our feet wet. Okay, let's do sine of 2x. So the biggest thing about the chain rule is to understand what a composition is. Can you write sine of 2x as f of g of x? Like in this picture, what is f of x? And what is g of x? So g of x is the function you plug in. And f of x is the function you plug into. Good, yeah, f of x is sine. Right, so in this case, what is the function I'm plugging in? I'm plugging in g of x is equal to 2x. What am I plugging into? I'm plugging into sine. Right, if I put them together, right, f of g of x is equal to sine of 2x. Right? Okay, so we have our formula now for the chain rule, is that f of g prime of x is equal to f prime of g of x and then g prime of x. So now that we have f and g, what other pieces of information do we need? Well, we need f prime and g prime. So what's f prime? Cosine, yes. And what's g prime? Two. Good. Okay, so now let's use the chain rule. So f of g prime of x is, okay, so we have cosine, which is f prime, and what do I plug in to f prime? What do I plug in? I plug in 2x, because g of x is 2x. And then g prime of x is 2. So that's the derivative. So in some respects, this is quicker. Right? This is our first example, so of course it's going to be a little slower since we're trying to understand. But if you think about it, the number of steps is a bit shorter. Any questions on that just first example there? Okay, let's do another one. This one's a bit harder to see. Sine squared. Okay, so we need an f and x. We have a, so for f of g of x, what's f of x and what's g of x? So write this as a composition. Okay, so, if you do that, let g of x equals x and f of x equals sine squared of x. I'm kind of stuck, right? Because I want to find f prime. But that's what I'm looking for. It's not x. I'll give you a hint. Okay, now what's f prime and what's f of x and what's g of x? Good, yeah, it's x squared and sine x. Which is which? Right, good. It's good to remember that x squared is a function, right? When you square something, you're actually doing a function. So let's just make sure we see that, right? What happens? What's f of g of x? It's equal to sine of x squared. Yeah. Okay, so we have f and g. What's f prime? Okay, f prime power rule is 2x, and g prime is cosine. So put it together, and we get, yeah, I believe that should be the answer. So it's f prime of g of x, g prime of x. F prime is 2x. So it's 2 times g of x, just sine. Right? This is plugging in g, and g prime is cosine. Oh, so not 2 sine x, we mean sine of 2x. Yeah, so is there questions about that one? Oh, f prime g. Oh, yeah. Yeah, this is good. F prime g is 2 sine x. Okay, any questions about this? So once you establish what the composition is, it's just being very organized after that. Okay, so this is what I like to do. You can find the reciprocal functions, trig functions, using the chain rule. Oh yeah, I promised, yeah, 8:30. Yeah, so let's take a 5-minute break. So if you want to keep on working, try to work on these. One here. So let's use the chain rule to find the derivative of secant. So last time we did it as the derivative of a quotient, but I think it's actually easier to think of it as a chain rule. Okay, so what's my f and my g here? What's the inside function? What's the outside function? So what is the function you plug in, and what are you plugging into? Yeah, so 1 over x, good, is the thing you're plugging in. And what are you plugging in is cosine. Good. What's f prime? What's the derivative of 1 over x? And I always like to think of it as x to the negative 1 instead of doing quotient rule. Right. Negative 1 x to the negative 2, or negative 1 over x squared, negative x to the negative 2, whichever you like. And then the derivative of cosine is negative sine. I've done that around 20 times so far, derivative of cosine. Okay, so the derivative is f prime of g of x times g prime of x. So you just plug everything in. So f prime is negative 1 over, you plug in cosine, because that's g, cosine squared, and then multiplied by g prime. Okay, so what is this? This is precisely, good, yeah, secant tangent. Yeah, so an alternative way to doing the derivative of secant, not by memory, using the chain rule. Yeah, I like this better than the quotient rule. Usually quotient rule is the one I like to avoid at all costs. Oftentimes I like to treat quotient rule as a product instead. So there's too many terms in quotient rule so I'm bound to mess up with quotient rule. So yeah, I think chain rule is easier. Yeah, so let's do the same thing for cosecant. Okay, so similar deal. We have sine is the thing you plug in, and you're plugging it into 1 over x. Okay, we just did this one, so the derivative is negative 1 over x squared. The only difference is that g prime is cosine. So the derivative is f prime of g of x, g prime of x. So f prime is negative 1 over, you plug in g, you multiply it by the derivative of g, which is cosine. So you get negative cosine over sine squared. And that's negative cosecant cotangent. So yeah, I like this better than the quotient rule. Okay, so any questions on these two? So using the chain rule to find the derivatives of these inverse trig functions. Okay. Let's do this one, cosine of cosine. What's f and what's g? Kind of a silly one. Yep, they're both cosine. F prime is negative sine. And g prime is negative sine. Okay, so f prime of g of x, g prime. So it's negative sine of what? Of cosine times negative sine. Okay, so two negatives cancel, and you get sine of cosine. And maybe if you want to make it clear, maybe put the sign on this side. Sine x times sine of cosine. Okay. Okay, so I think the main hurdle for a chain rule is just writing out your two functions, right? From here, it's just a formula, right? As long as you know what the formula looks like and how to apply the formula, that's the main point. I think you really need to understand what composition means and to understand this. Okay, questions? Okay. Should we do this one next? Or let's do this one next. Okay, what's f and g for this one? Good, yeah, so f of x is 17th. And then what's g of x is the other thing there, right? X squared plus 1. So what's f prime? And what's g prime? Good, f prime is 17x to the 16th. This is the power rule. And what's g prime is 2x. Good. So now you plug it into your formula. And we get 17, plug in g, to the 16th power, and then times g prime. Okay, so we're rearranging it to make it look nicer. 17 times 2 is 34. Questions? All right. Not at all. Actually, it's probably even better. Yeah, you can use, well, between, I mean, it's not the end of the, no, it's fine. What do you mean, like, yeah, that's fine. If you want to say, sure, if you want to say f of u is equal to u to the 17th, sure, g, or f of g of x is still going to be x squared plus 1. Oh, you want to do another one? Yeah, as long as you bring back the x, that's fine. I think it makes, I like it better with the u for f, just because that's the outer, the leftmost function. I think it makes more sense that way, but yeah, it doesn't matter. As long as you bring back the x in the end, it's fine. All right, let's do this one. Sine of 1 over x. Okay, what's f and what's g? By the way, sine of 1 over x is kind of like the opposite to cosecant. why is the opposite to cosecant? What's similar and different about the derivative of cosecant and the derivative of sine of 1 over x? Well, let's just, once we say f and g, you'll see the difference. What's f and what's g for sine of 1 over x? Yeah, they're not the same, but like they're close, right? How are they close? Like there's one main difference about sine of 1 over x and cosecant. Just list the f and the g, and that will illuminate it. Um, yeah, so I mean by the composition, they look very similar. The f is, for this case, is sine, yet the g is 1 over x. But notice that it swaps. Your f and g swap. That's just, it's a nice example, just composition is not swappable. Right? Sine of 1 over x is different than cosecant, right? This is a nice example of, oops. It's very important why you should get f and g right. Right? F of g is not equal to g of f. Right? You can't swap your composition because these are different functions, right? Cosecant and sine of 1 over x. So like if you wrote the wrong thing for sine or for f and g, you'll get the other thing. So just kind of notice that. Do you see what I'm talking about? Yeah, so it's clear about why it's important to do the correct one for f and g. Right, so this is cosine of 1 over x times negative 1 over x squared. So this is equal to negative cosine of 1 over x divided by x squared. Totally different than negative cosecant cotangent. Yeah, so if you flip-flop f and g, you get negative cosecant cotangent, which is very different. Okay, let's do some more and do a new page. I'll do one I didn't do over on that page. It's a good one. Let's do the derivative of secant of tangent. Okay, what's f and what's g? Yeah, secant is the f, and tangent is the g. And then the derivative of secant. Actually, let's make this a bit more interesting. What's the derivative of secant? We did this one last page, right? Secant tangent. Now, what's the derivative of tangent of x cubed? So I changed the number. I changed a little bit. What's the derivative of tangent of x cubed? How do you find that derivative? Absolutely, you can treat it as a composite function, right? So we have to do a chain rule. So if it's a composite, maybe let's use different letters. It's like u of x and v of x. What would my your f and g for your new composition be? Right. So the f would be tan, but I'm just using a different letter, and the vs is x cubed. Right. See, there's no harm in, we don't need a whole new derivative formula for composition of three functions, right? Because in the derivative formula we need a derivative, but we know how to find that derivative now by the chain rule. And what's u prime? Derivative tangent. So you don't remember, it's fine. This is secant squared. And then v prime is what? X squared. So now g prime of x is equal to u prime of v of x v prime. That's the derivative of this new composition. Okay, so let's do that. U prime is secant squared, and you plug in v of x, which is x cubed. Then you multiply by 3x squared. And you want to make it look nicer, so make it 3x squared. Okay, now you just put it all together. So now it's f prime of g of x, g prime. Okay, how do I plug in? Someone just write out for me f prime of g of x. I'll wait a bit because it's important to know how to plug this in. F prime is secant tangent, and g is tangent of x cubed. How do you plug in tangent of x cubed into f prime? Again, this is why understanding composition is important. Correct, yeah. So it's secant, so wherever you plug in the x, that's where you plug in g of x. and then multiplied by g prime, which is this thing we found here. Okay, so that's your derivative. So again, all you need to do is just find the derivative of various functions, and sometimes you might need more, and then plug into this formula. Okay, questions about this one? Again, this is kind of a good example of why you really need to be organized when you do the chain rule. There's a lot going on. Okay, let's do cosine of cosine of cosine of x. What's f and what's g? By the way, when you have a lot of different parentheses, I often like to alternate between a square bracket and a parentheses. So you can see which parentheses is meant to be where. Okay, what's f and what's g? Yep, cosine is f, and then what's g? It's the other stuff, cosine, cosine. Okay, what's f prime? It's negative sine. And how do you find g prime? Yeah, choose composite, and we have another chain rule going on. So u of x and v of x is cosine and cosine. It's negative sine, and v prime is negative sine. So g prime is u prime of v of x, v prime of x. Okay, so you just plug it in, negative sine of cosine times negative sine. So it's sine of x, sine of cosine. Okay, so now plug it into grand formula. And get negative sine of cosine cosine and then g prime is sine of sine cosine. Okay, so questions? Again, if you're very careful, this isn't bad. You just need to be very organized when you do these. Especially if you first start, like I think color coding is very helpful. You just see where everything's go, and just get practice. This is good practice for understanding what composition is. Okay, so the ones I really wanted to get to at the end, which I think we'll have time, are these. The derivative of x sine of 1 over x, and the derivative of x cubed sine of 1 over x. Okay, so how do you find the derivative of x sine of 1 over x? What rule do you need to use? Yeah, primarily this is a product. All right, so I'll just do the product rule. It's derivative of x, which is 1, times sine of 1 over x, plus x times the derivative of sine of 1 over x. We've done this one before. I'll just say what it is. Sine of 1 over x plus x, and then it's cosine of 1 over x times negative 1 over x squared. So this is sine of 1 over x minus cosine of 1 over x over x. Now, if you combine them, you get x sine of 1 over x minus cosine of 1 over x over x. And what's interesting to note here is that the limit as x approaches 0 does not exist. Right? Mainly it's because of this is the problem here. So in the if you look at x sine of 1 over x, so this is a problem we've explored a lot. The derivative, the slopes of the derivatives are not, or the slopes of the tangent lines aren't pointing towards a uniform tangent line. However, let's do this one, x cubed sine of 1 over x. So it's very similar. So it's going to be 3x squared sine of 1 over x plus x squared, the derivative of sine of 1 over x. So you have 3x squared sine of 1 over x. And then this one is x cubed cosine of 1 over x times negative 1 over x squared. So something interesting happens. Now this is suddenly, this limits to 0. Can someone tell me why this limits to 0? It's a squeeze theorem. See the x's in front of each of them? These make them go to 0. Yeah, good. And same thing for cosine, yeah. So this is interesting, is that if you graph x cubed as sine of 1 over x, well, you can graph it similarly to how you graph x sine of 1 over x by the bounds. Negative x cubed is between x cubed sine of 1 over x between x cubed. So you can graph it similarly. So it's kind of this oscillating picture. But it's approaching 0 very fast. So what's interesting about this one is that if you look at the tangent lines of each of them, well, these are really flattening out towards 0. Right? It's kind of interesting because if you take the derivative of the bounds, right, the bounds are approaching 0. But the derivative of these bounds are approaching 1 and negative 1 respectively. So that's interesting. So let's see if I can do this. I graphed these, and you can graph all these also. Can I do this? Can you see the Wolfram alpha? Can you see when I zoom in? Cool. Okay, so this is x sine of 1 over x. So this is the picture. So this is the picture of the squeeze theorem going on. It's between x and negative x. I think the recording, you can't see this. But now if you take its derivative, something weird happens. And watch this. This is the derivative of x sine of 1 over x. Well, what's going on at 0? I don't know what's going on. So the idea, it's oscillating so much around 0 that it's not approaching anything. So here we see the derivative doesn't exist around 0. Now let's compare this to x cubed of sine of 1 over x. So look at the difference between x sine of 1 over x. It kind of almost looks like a line around 0 versus x cubed. See how much it flattens out compared to x sine of 1 over x. This is still oscillating up and down a lot, while this is really flattening out very quickly. Right? This picture here would be the x cubed graph. Now the derivative of this is approaching 0. This has a clear limit to 0. So yeah, that's all we have for today, but I just wanted to show you that picture, really what the derivative is doing and, that limit towards 0. But yeah, I'll see you next time. I think you have some homework due tonight, and I think Wednesday, maybe. But I do recommend you do this. If you see a cool function on the homework, just graph it and see what it looks like, and kind of see if your derivative kind of makes sense. I really recommend you do that, especially when you have sine of weird angles. I think it's always cool to kind of look at. But yeah, have a good night, and I'll stop recording.